Hello guys, my name is Felix from examsconnect.com and welcome to our physics class. We are still on measurement. It's a continuation, and where we stopped last time, we want to ask ourselves what happens if you're talking of quantities that are being added, that are being subtracted, that are being divided, but you still want to calculate the error that occurs or uncertainty. So we're going to look at compounding uncertainties. Compounding uncertainties. Now, if two or more quantities are being added, let us start with addition. Addition and subtraction. If two or more quantities are being added or subtracted, how do we handle the uncertainty? Now, we say this, the total error or the total uncertainty is equal to the sum of individual uncertainty regardless of whether it was an addition or a subtraction. So in both cases, we usually have them as being added, the sum. The sum, you say that the total uncertainty is equal to the sum of individual uncertainties. The total uncertainty is equal to the sum of individual uncertainty. I want to give a small example. If that means that i.e. y is equals to a added or subtracted to b, then uncertainty of y is equals to the uncertainty of a added to the uncertainty of b. The uncertainty of y is equals to the uncertainty of a plus the uncertainty of b. You notice that in each case, I am dividing the absolute value divided by the actual value. Therefore, you notice that in both cases, whether it was an addition or a subtraction, I just have it as the sum. Let me give a more precise example. The perimeter of a figure is given as 15 centimeters added to 15.2 centimeters. The perimeter of a figure is given as 15 centimeters added to 15.2 centimeters added to 10 centimeters. This figure can be a triangle in this example where it has three sides. Therefore, somebody can ask you to calculate the total uncertainty or the total error in this case. So in this case, we are going to calculate the total uncertainty or the error involved in the perimeter as the sum of individual uncertainties. Therefore, for the first case, a half of the smallest place value is 0.5. For the second case, a half of the smallest place value, which is a 10, is 0.05, and for the last part, a half of the smallest place value happens to be 0.5. Therefore, in total, we get that the total uncertainty for this case is equals to 1.05 units. 1.05 units. Let me give an example that involves subtraction and see how do we get the total uncertainty in the case of subtraction. Look at this example. A quantity Q is given by the difference between 17 units subtracted 3 units. A quantity Q is given by the difference between 17 units and 3 units. Therefore, can you calculate the total uncertainty of Q. Calculate the total uncertainty of Q, or the error that is involved when you are subtracting these two numbers. So we have it as the total uncertainty is equals to the absolute uncertainty of the first value, which is, it happens to be a half of the smallest place value. Therefore, we get this as 0.5 added to the absolute uncertainty of 3, which happens to be also a ones. A half of ones gives us 0.5. Therefore, we get the total uncertainty as 1.0. You notice that regardless of the subtraction sign that I was using here, I still had to add the uncertainty, because we have said for the case of addition and subtraction, then the total uncertainty is the sum of individual uncertainties, and that's how we propagate the uncertainty during addition and subtraction. Now we go to the next part. What if we are multiplying or dividing? What if we are multiplying or dividing? That is part B. What if we are multiplying or dividing? So part B, it involves multiplication and division. Multiplication and division. Multiplication and division. And we say that if a quantity x, if a quantity, or even any value, you can give it any value, if a quantity is gotten by multiplication or division of other quantities, if a quantity is gotten by multiplication or division of other quantities, then the total uncertainty or error, the total uncertainty or the total error is gotten by adding the fractional. It's gotten by adding the fractional errors. It's gotten by adding the fractional errors or percentage uncertainty, i.e., we can write it this way. If y is equals to AB divided by C, if y is equals to AB divided by C, we notice that the quantity A and B are a product. They are being multiplied, whereas quantity C in the denominator is having a division. Then we can have that the uncertainty of y, as uncertainty of A divided by A plus the uncertainty of B plus the uncertainty of C. Remember that for each quantity, we get the uncertainty by dividing the absolute divided by the actual value. Therefore, the uncertainty of y will be defined as the uncertainty of A added to the uncertainty of B added to the uncertainty of C. Let me give a rough example. A quantity H is defined by 2.0 times 1.0 divided by 0.5. A quantity H is defined by 2.0 times 1.0 divided by 0.5. Then you are told to calculate the uncertainty of H. What is the uncertainty of H? And since H is gotten by the product and the division of quantities, we are going to apply this notion that the total uncertainty in the case of multiplication and division is given by adding the fractions of individual uncertainties. So we are having it as, we can solve it as solution. The uncertainty of H is given as uncertainty of the first part, which will be equals to the absolute 0.05 divided by 2.0. You notice that now I've changed. The absolute is now catering for the 0, since 0 means it is part of our recording. We need to consider it as the smallest place value. So we are no longer having 0.5, since we have a 0.0. I need to consider 0 as part of our place value. So it will be a tenth, and a half of a tenth gives us 0.05. We add that to the second absolute uncertainty of the second value, 1.0. So that will be 0.05 divided by 1.0. Then we add it finally to the last part, 0.05 divided by 0.5. So the sum of these uncertainties, each individual uncertainty, will give us the total uncertainty of the quantity H, the total uncertainties of the quantity H. And if we work out further, we get this as, for the first part, 0.175. 0.175. Now, this is the case where we have addition of quantities to create one individual quantity, and multiplication and division. What if our quantity involves a power? Now, so this one is C, where a quantity involves powers. A quantity involves powers. If a quantity is being raised by an exponential power, if a quantity is being raised by an exponential power, then the total uncertainty is given by the absolute, is equals to the absolute uncertainty multiplied by the power that was raising the quantity, is equals to the absolute uncertainty multiplied by the power that was raising the quantity. And if I may give an example for more understanding, it means that i.e. y, for example, y is equals to a power n, y is equals to a power n, where n can be any integer, then the uncertainty of y is equals to the absolute of the product of n multiplied by the uncertainty of a. That's why we are saying the absolute uncertainty of the quantity multiplied by the power. Therefore, if y is equals to a power n, then the total uncertainty of y is equals to the absolute of the product of n being the power that was raising, multiplied by the absolute uncertainty of quantity A. Remember, quantity A makes up value Y. Let me give an example on the same. A quantity, example 1, involving powers. We want to see what happens if a quantity is made up of a power. So we have this as a quantity W is given by 2 raised to power 2. 2 raised to power 2. Or you can even have it as 2 power 0 raised to power 2. 2 power 0 raised to power 2. Calculate the total uncertainty. Calculate the total uncertainty of the W. And in our solution, we have it as total uncertainty of W is given by the absolute value of the power, which is 2, multiplied by the absolute uncertainty of this value that was being raised. So I'm going to have it as 0.05 divided by 2.0. Now that gives us 2 multiplied by 0.025, giving us the value as 0.05, and that will be our total uncertainty for the case of this W that we are given there. So having been able to propagate each error or uncertainty, you can solve any question that is involving addition, multiplication, and also powers of uncertainties. And remember, in every measure that you take, there is always an error, either due to human error or even the machine error. And you always need to consider this, because it's not likely for us to get ideal measures. You'll say that ideal measures may not be present due to the kinds of instruments that we use. So for every measure that you take, always consider the uncertainty involved. May it be an addition, may it be a multiplication, or even a power. Meaning that if you are to calculate the area of an open football pitch, when you're coming down to solving it, let me use that also as an example. So if you are given an assignment, maybe you've prospered in your career and you are given an assignment to calculate the area of a football pitch, you need to consider the uncertainty involved in the measures that you are taking. So consider this. The following are the records of a football pitch, and you are trying to consider the area. So we have on one side, we have 17 foot versus 10 foot. This is just an example. It may not be to the exact value, but we want to see how do you put the uncertainties in your sample size. So in the solution, we first come and define the area as length times width, and therefore we get the actual area as 17 multiplied by 10. Therefore we can have it as 170 foot squared. However, this is bound to be affected by the errors when you're using the machines. Therefore, we come and say that, however, we have an uncertainty for the area as the sum of individual uncertainties. So for the first part, we are going to have this as 0.5 divided by 17 plus 0.5 divided by 10, giving us the total uncertainty as 0.079. Therefore, our answer in terms of the area should be given as 170 feet squared plus or minus 0.079, plus or minus 0.079, in case you want to consider the uncertainties that are involved during the measure. So with that, I want to end at that, and thank you for watching.